All right, thanks everybody for being here last day of the workshop. Great experience so far. Thanks to the organizers, Sophia and Patrick, for the invitation. So this talk is about vector autoregressive models. We have already seen applications and versions in a number of talks. The first day by Eric, where essentially he tried to extend to a multi-change point vector autoregressive model. In Danielle Bassett's work, she combined vector autoregressive models with control, going back to structural controllability and other ideas from adaptive control for neuroscience applications, and also in Veronica's talk on sort of gene regulatory type of networks. So I think a better title of what I'm going to do this morning is an excursion in Varland. I'm going to discuss the classical model and especially focus on a lot of the theoretical properties, because there are a number of interesting challenges once you move to the time domain when you have time series data. And then some extensions, some new models that we have looked at, and essentially everything is sort of motivated, and my personal excursion in this Varland has been through a lot of applications, and I'll tell you how I came to this problem. So lots of topics to cover, and some of this is sort of the standard things that we have learned so far. I'll show you a kind of acute application on financial network connectivity. It's a topic that, if you look at financial econometrics journals, there's a lot of activity, lots of preprints on the equivalent of the archive for social scientists, the Social Science Research Network. My excursion to really dynamically evolving networks is going to be VAR models and change point analysis, say a few things about some theoretical aspects, and some current work. So actually, vector autoregressive models, I mean, of course, there are standard tool in time series, but a lot of the work in the 60s came from control theory, both in the work of Kalman and then a whole bunch of other people, both in terms of structural controllability that we heard on Tuesday's talk in neuroscience, but also adaptive control, especially for linear invariant systems with quadratic costs. This is the LQR controllers. Great results, and also great applications in engineering. And then in the 70s and the 80s and in the 90s, essentially, apart from some standard developments in statistics, most of the work has been in econometrics, and I'll explain why on the next slide. And in the 2000s, in the mid-2000s, once we start having all this microarray data, people started thinking, and they start producing also time course data, people start thinking of using this type of framework for reconstruction of gene regulatory networks, and we heard the talk by Veronica. And the latest thing that we heard a number of talks is neuroscience data, study functional connectivity, and so forth. So as I've already mentioned, historically, finance and economics, or better, economics and finance, was a big impetus for applications of vector autoregressive models. And actually, the most important paper is by Chris Sims, who won the Nobel Prize for his work on VAR and connections to economics in 1980 in Econometrica, where, first of all, he moved away from the previous framework of, or he incorporated ideas from the previous framework of dynamic stochastic general equilibrium models that are very difficult to test, and do empirical work on them, and used ideas from those type of models and incorporate them in a VAR framework, and he explained why this is much more important or useful for empirical work. And after that, of course, the economists were up and running, and they started sort of incorporating or using VAR models in a number of other areas. This is one of the first papers that I've seen in finance, maybe there are earlier ones. And of course, one of the reasons that this model is very useful to economists is that, once you start sort of introducing shocks to the system, and unfortunately I'm not going to have time to discuss that, they can start thinking of how government policy or other intervention policy, in this particular case, they're talking about government spending and taxes on output, so this is kind of intervention to the system. You change some policy regime, and similarly, of course, Ben Bernanke was until recently the chair of the Federal Reserve Board in the United States. He was interested in monetary policy innovations, essentially once you start controlling the federal funds rate. So This is the simplest model that people have used in economics, these three key variables, and this is one policy variable that you can tweak. So that's why, understanding how these three key variables that capture employment, consumer price index, and the federal funds rate interact, and of course they're used both for forecasting purposes, but also again when you start tweaking one variable to see what policy changes induce to the system. I'm not going to say much about functional genomics. We already had a talk. And this was one of the first papers in bioinformatics that I found using this type of framework. Although here, from a technical perspective, the way they used vector autoregressive models and associated ideas from Granger causality that Eric mentioned on Monday is a little bit weird in the following sense. So here you have P genes and data over time, but the way people in bioinformatics have been using this modeling framework is as follows. You take any of two genes, and then you fit a two-dimensional VAR model. And essentially, you run the classical Granger causal test to see if, by including additional information from this gene, you can better predict the behavior of the other gene. And therefore, you do that for all pairs. And of course, given the fact that you're doing you estimate gazillion of parameters, you need sort of, at the end of the day, to do some multiple comparisons control, to control your family-wise error rate using one of the standard procedures. Why am I saying that this is a little bit weird? Because, once you only use two at a time, there are all these other influences from all the other genes, and this is not kosher. Essentially, you're not doing sort of the right type of conditioning, and therefore, you can easily show, and this goes back even to the work of Granger, by omitting all the other variables and the influence of the other variables, but the estimates of these networks are inconsistent or biased. And the latest application is in neuroscience, and we had already a number of talks that discuss the subject. So why the need for suddenly to start thinking about high-dimensional VAR models? As you can see, or as we're going to see in a couple of slides, for every p-time series, your parameter space grows at the rate of p squared because you're trying to estimate all these cross dependencies, and then it also grows linearly as a function of the lag of the process, if you have more memory. For a VAR1 system that current observations only depend on the previous time point, you have p squared parameters, but as you start putting more memory, and this is important on many applications, your parameter space grows at the rate of dp squared. So you can easily see that, we heard talks where there were 40 brain regions that they wanted to understand. So at that point, and you start having thousands of parameters, and you may not be able to compensate with adequate time points. The other reason, I'll give you, so for functional genomics, you have the same problem, hundreds of genes. For finance also, you can have hundreds of stocks. So naturally, you have very large parameter spaces. But even in more classical econ applications where you constrain yourself to the 10 most important macroeconomic variables, people found out that by looking at very small systems, sometimes the signs of the parameters that they get do not agree with theory, and they found out that by increasing their system and therefore studying more macroeconomic variables together, they have better forecasting abilities and a better understanding of the relationships. So there is definitely a need for understanding what happens for high-dimensional VAR models. So there are two modeling regimes. The majority, actually all the talks that we heard are in this regime, what I would call the panel VAR setting, that has also been looked in econometrics for small p, for small number of time series, where depends on the setting. For example, in functional genomics, t is very short. 5 time points, 10 time points, maybe 30 time points. On the other hand, as we saw in the talks in neuroscience, t can be very large, even to of the order of thousands. But the other thing that you have is in panel VARs, you have multiple experimental subjects. So you have replicates. You have several animals, or you have replicates of your cell line, or you have several patients when you do neuroscience. The more classical framework that, of course, you have t relatively large, because otherwise you're not going to have enough data, but you only have one replicate, is the typical econ or finance setting, because there is only one realization of the economy or the financial system under consideration. And this poses a few more technical challenges, because here essentially you have a lot of dependence. Again, depends on how strongly temporally dependent your system is, whereas here you can definitely compensate because you have independent replicates, and therefore that essentially enhances your sample size, intuitively speaking. So just to recap as an introduction, VAR models have been a canonical model for understanding lead-lag cross dependencies for a very long time. And for short horizons, they have been very successful in many forecasting purposes. And when I say short, I mean really, really short, 1, 2, maybe 3 time points. Once you start trying to go further out, I haven't really seen many successful applications. And of course, in economics, through this impulse response business for intervention analysis, when you change a variable in the system. But as I've already alluded, this temporal dependence exhibits a number of technical challenges in high dimensions. So in the next few slides, I would like sort of to walk you through some of the technicalities and what we have learned, and what's the state of the art right now. So let me show you the VAR model. So this is the VAR model. We have p-time series, and the values at time t depend on previous values, either of the same time series or through other time series. So essentially, these are captured by these p by p transition matrices that are the directed lines. What we allow in the model, because this is very standard in econometrics literature, you can have additional contemporaneous dependence. Essentially, your error term can be exhibit correlations, and these are captured by the dotted red lines. Of course, in the high dimensions, we need sort of to start making assumptions that we have either sparsity or low rankness, because otherwise we have a lot of parameters and we don't have adequate data. The only assumption that we're going to make, which is very, very standard, is a stability assumption. Essentially, the eigenvalues of this characteristic polynomial lie outside the unit circle, which ensures stationarity and so on and so forth. So this is the minimum assumption that you can make in order sort of to have a properly defined VAR model. I'm not going to say much about the selection of the lag in this talk. I'm always assuming that using one of the usual methods, like an information criterion, AIC, there is Hanan's criterion, there are other criteria that people in the time series have come up to have a consistent estimate, and essentially the results go through. But I'm going to briefly discuss some new work that people at Cornell are doing of sort of incorporating more information of how to select the lag. So just a brief detour, given the fact that Eric mentioned the notion of Granger causality. And for example, in functional genomics, you never see the word VAR in the paper. Everything's about Granger causal networks. On the other hand, as we heard in neuroscience, actually they use the term VAR. So this goes back to the 1969 Econometrica paper by Clive Granger. And essentially the concept is that, if you incorporate all these additional variables to predict the values of one of your time series. So here I'm going back to the original paper. Essentially, we have 2 time series, y and x. And if you can show that by incorporating lagged values of the other time series, essentially, these cross dependencies, you can do a better job in predicting future values of y, then we call x Granger causing y. And of course, under a lot of additional assumptions carefully discussed in the paper and subsequent work, you can start sort of making really causality statements. Given, in most cases where, so Granger causality essentially is based on statistical associations. If you really want to make Granger causal statements, you need a lot of additional assumptions, which essentially in most practical applications don't quite hold. You can think of a different way about this, essentially is trying to estimate a direct acyclic graph. These are your directed edges, but it's a nice and very simple direct acyclic graph to estimate because your variables are ordered. So essentially you have a linear ordering, and therefore everything is nice and simple, and automatically you have a polynomial complexity algorithm, essentially a least squares algorithm. That's where otherwise direct acyclic graphs, if you don't have a known ordering of the variables, is a very hard problem. Anyways. Okay, a few things about estimation, and there is nothing new here. Essentially the way you do it is you pack your data appropriately and you create these matrices. This becomes your response. Essentially you take all the times appointee for all the variables, you pack them together, and then similarly you start creating your design metrics. You do the same for all the transition matrices, and then you vectorize them, and lo and behold, at the end of the day, once you carry out all these algebraic manipulations, you end up with a least squares model. So that's very known and very standard. And of course, in our case, given the fact that we assume high dimensional scaling, we need to put some assumption of sparsity, so this is very natural. So at this point, as you realize, essentially I have transformed the problem to a penalized lasso regression problem. However, there are a lot of caveats, because as you can see, this is a very tricky design matrix because it exhibits dependence both between rows and also between the design matrix and the error term, and this is not the usual setting of lasso regression under IID assumptions. So suddenly all this suggests that maybe there are technical challenges that are peculiar to this particular problem.
George, are you using the L0 or the L1 norm?
No, this is just for the definition. L1 comes on the next slide. Thanks, Ernst. So if you don't assume any contemporaneous dependence, so this is sigma square, so you don't assume all these other additional red arrows, then this becomes an L1 penalized regression problem, nothing special there. But on the other hand, if you believe that you have additional contemporaneous dependence, and that was in the application that Veronica showed us, at that point, essentially, you deal with a penalized log likelihood. And this becomes much more involved because you recognize this generalized least squares type of criterion, and then, of course, the standard L1 penalty. The first problem is very easy, very nice. Essentially, the criterion function decomposes, so essentially you have separability, which essentially boils down to you pick one response at a time, one of the time series at a time, and then essentially you regress it on all the available regressors, and you can do that in parallel because essentially your objective function is separable. So there is no reason to keep them together. So this is very nice and neat. It boils down to standard regression. There is nothing more to say. So this you can run on very, very large instances, provided that you have adequate data. The moment you start having contemporaneous dependence, obviously all the regressions coupled together, so you lose the separability. So Richard Davis and his group, suggested of doing it sort of this obvious way. The problem is, there's nothing wrong with it, but the moment you start having a fairly or a reasonably large or a moderate large P, this starts becoming very, very large matrices. So, if your P is 100, at some point, definitely on my laptop, which is pretty old, you cannot run it. Maybe on your laptop, which is the latest technology, you can still do it. But for a larger P, at some point things break down. However, of course, a lot of you will recognize that why don't we play the usual game? Estimate sigma epsilon, and then go back and estimate beta, and then iterate, and so on and so forth. There is a small catch there. That's exactly what I'm showing you on the next slide. So essentially, do a block coordinate descent, iterate between the two steps of estimating the regression coefficients, essentially the directed arrows, your transition matrices, and then using the residuals, estimate the inverse covariance matrix. Of course, again, you need some assumptions of sparsity. So you go between the two blocks, and you can show that especially this step can be implemented in parallel, and then you gather the residuals, and you do one big estimation. But this is definitely nice, and essentially, I think Veronica more or less put the same algorithm on the board. However, from a technical perspective, there is a catch, and you need to be careful, especially if you're asking for the maximum likelihood estimator. If you're just going to run it once, you're fine, and then the theory tells you some properties about beta hat and sigma hat inverse. But if you really want the MLE, eventually, you need to start iterating, and the objective function is jointly non-convex. And the moment you lose convexity, and at the same time you have these non-smooth penalties, life in optimization land becomes more challenging. And however, this problem is still nice. If you lose convexity, the next best thing that you hope for, and this holds here, is bioconvexity. So essentially, if you fix the B's, you have a convex objective function as an argument of the inverse covariance matrix, and if you fix the inverse covariance matrix, some estimate, you have convexity in terms of B's. And therefore, what we have in this recent JMLR paper for a chain graph problem, a little bit more general formulation because we were coming from a different application in integration of omics data, but we have a chain graph type of model. We can show actually convergence to a stationary point, provided you initialize the algorithm at a good point. What is a good point? It has a lot of technicalities that you can see in the paper, but essentially it suggests that as long as you have a biconvex function, it doesn't generalize to triconvex. So if you have triconvexity, or things don't go through, but as long as you have bioconvexity and you have good initialization, and you also can guarantee things of how the algorithm iterates and it doesn't escape a nice ball around the truth, then you have both convergence and all the nice properties. So this is kind of an aside, but we found this to be useful, and we're going to use a similar idea much later when I showed you an extension of the VAR model. Okay, I know that it's still early in the morning, but bear with me some of the theoretical considerations. And the way I got really involved in this theoretical consideration was I came to the VAR models from an application on functional genomics. So I have seen the previous work in bioinformatics where they were doing it this pairwise fashion, and of course this is not kosher. And I said, okay, let's throw the full model, develop some algorithm. And then we looked at the literature to see what was known about essentially lasso regression estimates under temporal dependence. And the only thing that we can find was a small corollary in one of Wainwright's papers. Okay, and then we did some epsilon extensions. But then when we start simulating in order to see if our algorithm works well, essentially the algorithm kept working well under settings where the theory said that we shouldn't even be getting consistent estimates. So the first reaction to the student is, you don't know how to simulate, or your code is wrong. It's the easiest thing, always to blame, And after a month of going back and forth, I start suspecting that maybe the conditions or the available work in the literature was too stringent, and we need sort of to take a new look. So since I have built the suspense, let me tell you, where things are going. Okay, this is a kind of a background slide. Essentially, these are by now the two standard conditions that in some cases people do an epsilon variant of this known as restricted strong convexity, but essentially they have exactly the same intuition. This puts constraints on the Gram matrix over the submatrix of the support of your beta vector where you have the non-zero elements. So, and that's where essentially the restricted strong convexity comes in as a variant of this condition. Essentially tells you that the Gram matrix over the support of the non-zero coefficients need to be sort of well conditioned. And then you have a deviation condition. It's exactly the same type of conditions that we use for low dimensional models. You need some condition on the X prime X matrix and a condition on the X prime E. And these are the, the way we work for IID data. And then we have this famous estimation rate. These parameters, the tolerance of the restricted eigenvector, eigenvalue condition, and this parameter of the deviation condition come in this factor. And then your rate scales up. K, remember, we have K non-zero elements, so K over N, this is sort of the parametric rate for estimating K non-zero parameters, and log P is the price you pay because you are in this high dimensional scaling. So all these are by now very well understood. However, there are a few issues when we move to time series domain. given the fact that we have temporal dependence, are these conditions satisfied? Therefore, can we make those assumptions? If you use fixed designs, of course, it's an NP-hard problem. There's some work in the literature. And for a random design matrix, and remember here I have Gaussian assumptions. So Raskuti et al. Showed that it holds under when your samples are independent, so your conditions hold for IID Gaussian data, and Trudelson and Zhou have an extension for sub-Gaussian distributions. So as long as your data are IID, essentially by now everything is known, you can make those assumptions, and then under those assumptions you can show consistent results. However, especially for the VAR model, everything breaks down. Rows are dependent, of course, columns be dependent, that's okay. And also the error term and the design metrics exhibit dependencies. So suddenly, the nature of the model imposes all these dependencies, and we don't know what happens. And essentially, this is what's demonstrated by, all these red entries. So this was the paper that had in one of the corollaries the only condition we could find, and essentially, it's the natural condition that, if you have a single autoregression, you assume that the autoregressive coefficient is less than 1, because essentially this is equivalent to the stability condition that we started with. But if you're trying to sort of find the natural analog for a multivariate time series, essentially you make this assumption on the operator norm. It turns out, and that's where the simulations were giving us different results than what the existing theory told us, was that as P increases, this becomes a super stringent condition. And essentially, this starts becoming degenerate, and you can only have a diagonal A matrix for all practical purposes. So you cannot afford under this condition, when P becomes fairly large, non-diagonal entries, and eventually that means that essentially you cannot really estimate cross dependencies, which is the main point. So what to do? Well, the answer was hidden by going sort of into the frequency domain, and then essentially everything works nicely there. And given the fact that still, this is still a limiting part of, a limiting component of this work, because we assume everything Gaussian, we have some minor extensions, but we cannot really get very good bounds, and that's a lot of problems in time series analysis. So in this particular case, under the Gaussian assumption, and they assume that the VAR process is stable, which is the minimal assumption as I mentioned, then the spectral density has a very nice closed form, and you see how nicely the two sources of dependence factorize. This essentially captures the temporal dependence, and this captures the contemporaneous dependence, and that will allow you to do a lot of manipulations. So, okay, so how do we quantify the dependence in the spectral density? For single time series, usually we plot the autocovariance function, but another way sort of to think about how much temporal dependence we have for a single time series is to look at the spectral density, and these images have sort of a different or an opposite behavior. In the autocovariance function, if you have essentially very limited temporal dependence, it goes down very fast, and as your autoregressive coefficient increases, the autocovariance starts decaying more slowly. On the other hand, the spectral density for very limited dependence essentially is flat. You have a flat spectrum. On the other hand, as you start packing more temporal dependence, it becomes more and more peaked and becomes singular, once you cross the unit circle. So for multivariate processes, essentially, you are trying sort of to capture the same type of behavior, and this is played by the maximum eigenvalue of the corresponding matrix valued spectral density. And here I have sort of the corresponding definitions, and especially for stable var1 processes, there are very nice and explicit expression of how it scales up with the spectral radius. Actually, in this particular case, so the maximum eigenvalue essentially captures the stability and essentially captures how much dependence the system packs. But the minimum eigenvalue is also very important because it tells you how much cross-dependency you can afford. If you start having too much cross-dependency, then minimum eigenvalue starts getting very close to 0, and then you start having other problems. So essentially, roughly speaking, this cannot grow too fast, and this needs to stay away from 0, and then you are sort of in the nice regime. So my point is that given the fact that temporal data have all these intricacies because they need to satisfy these additional assumptions so that you have stationarity and all these other nice properties, you have much more limited room and you need to be sort of careful of how to operate. So this is the key result, and essentially all the proofs are based on this one. So you may recognize that essentially this is a variant of a Hanson-Wright type of inequality for quadratic forms, and we have for the own terms and then for cross terms, and then some additional results. So essentially, this is the main tool that we had sort of to develop, and then everything else sort of follows with some additional technicalities from existing results for IID data. And actually, we're going to see in a couple of slides a very nice interplay what happens when you have temporal dependence and how they relate to results that were known for IID data. So everything, for at least for Gaussian, looks very nice and neat. So, and here is sort of the result for a VAR-D model. The only assumptions that I make, of course, I need the Gaussianity because then I have all these very nice explicit expressions. And the only assumption we need is stability. The scalings are very standard. And if you look at the rate, this is exactly the rate that I showed you for the lasso regression, given the fact that we have essentially a fancy lasso regression problem. So this is exactly the rate that you would have for IID data, and everything that comes from the temporal dependence comes about in this term. And this term, once you write it out in its full glory, you see that it becomes large when your temporal dependence starts becoming large. It scales up in this way with a maximum eigenvalue of the matrix valued spectral density, or this becomes very small when you have a lot of cross dependence. So, for example, just to give you some idea, you cannot sort of estimate, you cannot have consistent estimation if there are the following two conditions happen, which come out of, when you look a little bit more carefully at this term. So here is t, and here is t minus 1, and let's say we have a var1 model. So if I have this scenario, then you cannot have consistent estimation. Essentially, you have a dominant node, and therefore this essentially gets screwed up. The other case where, again, you cannot have a consistent estimation, if this happens. Sorry. One node is influenced by everybody else. So the first case is much more intuitive because essentially, in that case, you have sort of a dominant node that impacts everybody, essentially drives, is a strong driver of the system. But also, if you also have a node that is influenced by everybody else, again, that breaks down the consistency. And this is sort of a sufficient condition related to the minimum eigenvalue. So essentially, you cannot have very dominant nodes or, on both sides. Yes?
So, but your condition is only sufficient?
Yeah.
Okay.
Yeah, no, this is a sufficient condition. At least, we work it out in order to start getting some intuition of how these things, this is just a sufficient condition, absolutely. But actually, in the low-dimensional literature, there is a paper by Pesaran and one of his students, I think it's been published in Journal of Econometrics, where they studied a special case where you have exactly this case, but you're in the low-dimensional case, and you need to do a lot of additional work when you have a dominant node that impacts all the system, and it's still not entirely trivial, and you're still in low dimensions.
So if I understand the picture correctly, you're essentially saying that could you impose conditions on the number of non-zero entries in the various rows of the A matrix, and is that a sufficient? Because that would seem to be maybe easy.
Hold on to that. This is work that other people have built on. So I'll give you some references. Yeah.
Remind us what a K was?
OK is the total number of non-zero elements across all members of the transition matrices. So when I packed it into this big vector, regression vector, when I did the transformation, I'm assuming that the total sparsity is K across all your lags. So essentially, it's the number of elements that you're not that you're trying to estimate, and dp square is the way the parameter space grows. So essentially, this is exactly the equivalent of log p in the standard regression. So everything here is exactly the estimation error for the corresponding problem for independent data. So essentially, you see that how the convergence rates are governed. We have these dimensionality parameters, and then all these internal parameters that come from the conditions are part, in this case, of this more complicated term. So here, you not only have the information that comes from your spectral density, but also how the restrict eigenvalue and deviation condition can. Yes, Andrew.
Could you say intuitively how the decoupling takes place? Are you essentially able to appeal to existing results by first extracting whatever phi is capturing, and then can you appeal to existing results to get the second term, or you have to, in terms of how the analysis goes, just wondering how the separation takes place through that?
Through that, and then through existing results. You do the usual KKT conditions, you know exactly. But you see the nice form of the spectral density under Gaussian is a very big help, because you have a very nice explicit manipulation of the beast. Yes. Yeah.
So not in time series context, but in longitudinal data, there is a sort of regression problems with the large N, large P, that you have this design matrix condition of eigenvalues. Are they somehow related?
Yeah, essentially, give me a couple of slides. Essentially, similar things go for the panel var, because at that point I have both replicates and also I have time points, and the conditions look a little bit better because you have these independent replicates. So the other important thing that we need to show, and actually it goes through, and I don't want to put pages and pages of Greek letters. Essentially, the other important thing is that these restricted eigenvalue conditions and deviation conditions hold with high probability for stable Gaussian var processes. So lo and behold, just to recap where we stand right now, if you make these standard assumptions for stable var models, essentially you can establish the consistency of the var estimates. And but the important thing is, for stable var models, Gaussian models, then you can show that these necessary conditions hold with high probability, and we've already discussed how the convergence rates behave. So here is sort of the interesting thing. Essentially, a lot of people have taken this basic concentration result that we established and run with it. So right now there is a proliferation of different papers. So regression with temporal data and lasso, but then they start looking at non-convex penalties, sparse covariance estimation with time series. We did this work with the group lasso in the form of a panel var. The question that Andrew asked, there is some work on hierarchical var models by people out of Cornell, where they are trying sort of to put particular constraints on, additional constraints on the transition matrices, so to say that maybe the transition matrices decay, so the influence from lag 2 is smaller than the influence from lag 1, and so on and so forth. So a lot of people have started sort of playing with variations of the var model. Also, this paper by Kathy Ensor and her collaborators down at Rice, where they put local dependence because they come from more a spatial type. The time series sit also on space, and therefore, they have these local constraints. So all of them, essentially, all these results have, from a technical perspective, have this common theme. But your estimation error for dependent data, and this, and also tensor regression with dependent data. So nothing to do just with var. The Gaussian assumption is still important. Essentially, the estimation error decomposes to whatever we knew for IID data, and then something that captures how the measure, the narrowness of the spectrum behaves. So this is kind of nice because, if you can guess, or if you already have work for problems with IID data, then it seems that this is sort of a general theme. I don't know how far you can push it. At least this starts giving you some insights of what the results should look like and so forth. Actually, this is an interesting paper. It's still on the archive because as a special case of their big framework, they showed that the estimation rate that we have actually is minimax. So this is a further extension. I'm not sure if anybody's going to ask the question, what do we know going outside Gaussian data. You can have, we have done a little bit of work and we have started seeing something like that, but this is not very well characterized because you don't have nice expressions. There is some work on Poisson VAR models out of Wisconsin, Garvez Rashkuti and his collaborators. They start seeing, I think, if I paid enough attention to his presentation, I think they start seeing similar type of results, but their conditions are somewhat similar to what we came up with.
Because there's general situations where the Fourier transform becomes Gaussian even.
Yes.
So then you should, as long as the tails of the distribution
Exactly.
are not too horrible, it should just go straight
Exactly.
through.
Exactly. But I haven't seen anybody sort of taking this very general point of view and putting the most general framework. But yeah, people have played with a lot of other norms, other penalties and so forth, and this seems kind of a neat general phenomenon. So just one word or a couple of slides on panel VARs, given the fact that I have a number of other slides. So this is something that Eric alluded in his model where he wanted to put more structure. So in this particular case, we just looked at the panel VAR, but we put group sparsity because we were motivated by an application in genomics. So your groups come from pathways, so you have all this prior knowledge. Potentially similar ideas are applicable to neuroscience. And essentially, you can turn the crank, you get better rates as long as your groups are appropriately identified. So essentially, this is your VAR model, but here you assume that all these variables behave in a similar way because, let's say, they belong to the same functional pathway, and all these variables behave the same way. So in that case, you can incorporate this prior information, and obviously your rates improve because you don't deal with p variables, but you deal at the rate of at the size of the at the number of the groups. So the only interesting thing that we have in this paper is what if your prior information is misspecified and how much misspecification you can afford, and we have a second pass through a thresholding. So there are some neat extensions. So let me switch a little bit to an application. This is something that has caught up in the financial econometrics community, so a lot of people are thinking about this type of problem. Essentially, trying to make connections between how connected the financial sector is and systemic risk. And of course, there are deeper economic reasons, but this is something that was discussed in this policy talk by then Federal Reserve Board Vice Chair Yellen. She became eventually the chair, interconnectedness and systemic risk. And especially after the financial crisis, this has become a big topic. So the interesting thing is that there is a lot of theoretical econ finance literature. The problem is that the very detailed models that they have developed require data that you're never going to acquire. They're not available. Even for the Federal Reserve Board or for the central bank of any country, they're never going to have that detailed knowledge of a bank's or an insurance company's portfolio at every point in time. So essentially, you need to have the full balance sheet at every point in time, and this doesn't happen in the real world. The nice thing, something that, I've been going to a lot of network conferences, and something that I've never heard in more stats or probability network conferences is incorporating strategic behavior, which is a very big thing for economists. So that's what I like from that literature. On the other hand, you cannot sort of do any empirical work. So the financial econometricians have, looked at the problem from another perspective, say, okay, what data are available? I think there was a similar talk on a previous workshop where the data were not the log returns of stock prices, but BDAX prices from derivatives. I think Barry Post presented that work. And the very popular, this is by now a very popular paper. It's approaching 1,000 citations, although it's very recent. Essentially, it uses the bivariate VAR model that people used in functional genomics to essentially estimate all these statistical dependencies between financial firms. So we looked at this problem by throwing the full VAR model, and we did a little bit more work. Of course, you need to sort of pre-process the data. And then essentially we fit a VAR1 model. We looked at larger lags. It didn't make a big difference. The main development here from a more technical perspective is, once you get the estimate of the transition metrics, you don't have any idea about some uncertainty quantification. And this is a very new development in the stats literature of performing bias correction because you're having a lasso, and then that gives you marginal p-values. So for IID data, there is this paper, and there are a number of other papers by Sarvani here and collaborators, where they do this bias correction. Essentially, you are trying sort of to come up with this adjustment, and this adjustment comes by solving this minimization problem. These are the corresponding columns of these metrics. So the main thing that we had to do is, again, work through some martingale theory in order to show, given the fact that we have temporal dependence. But lo and behold, essentially turning the crank, apart from some technicalities, you can show you get asymptotic distributions for each of the elements of your adjusted transition metrics. So right now, once you have these p-values, then you can use a Bonferroni type of correction or a FDR type of correction, to control your family-wise error rate. So this starts getting kind of important for some applications. So this is what we did in this particular case. And of course, one of the problems once you estimate these complicated VAR models, you're trying sort of to summarize the information and see what on earth is going on. So we summarized, once we get our estimate of A, essentially we looked at the total number of edges or another network measure network parameter, sort of to come up with a summary statistic. So this is a period that I'm showing you is not chosen completely at random. The reason is this covers the financial crisis. This is what the picture that you get by just doing the pairwise Granger causality, even after adjusting for multiple comparisons. Essentially, it's very difficult to see what goes on. Suddenly, once you put all the information together in this gigantic VAR model, you start finding some players that eventually expose. We know that they played an important role in the financial crisis. To me, it was a little bit surprising that AIG, but eventually had to be bailed out at the tune of $180 billion by the American taxpayer, was showing up in such a very simple monitoring system quite a bit earlier. It started sort of becoming, Goldman Sachs was sort of fairly known, even, it was an important market player. But AIG, being an insurance company, people didn't really understand how insurance was, through the derivative business, so intimately related to financial companies. And then if you look at the entire time period, essentially, once we monitor some of these parameters that come out of this estimation, we can identify peaks that you can eventually relate to important financial distress events. Is that the end of the story? Of course not. But, you need a lot of other information to really monitor the financial system. But, if you do things properly and in a rigorous manner, essentially you start getting enough information that can be just another part of your toolkit where you're trying to address such a complicated problem. And then you can also start understanding intersectoral connectivity and so forth. But this is sort of an application that a lot of people are looking at, given, of course, its importance. This is the only thing that I'm going to tell you about dynamically evolving VAR networks. Essentially, this is what Eric's talk was about. I'm only going to have a single change point because when I have multiple change points, I don't even know how to handle it. Eric had a very nice solution. But so essentially, here is the model. Before the change point, you have one transition matrix, and then the dynamics change to another transition matrix. So the cross dependencies change after a change point. And you assume that you know that a single change point exists in this world, and there is nothing else going on. So the key aspect is, what can we say about the change point? And these are the things that we know for the low-dimensional models. Essentially, the key aspect that we know is, this is a simple stamp model. The key aspect that we know is that the rates are very fast. It's of the order of 1/t. Essentially, if you have enough signal from when you change from this regime to this regime, essentially you can trap the change point in the neighborhood of the order of 1/t, which is essentially the order of your data. So we know that these problems have really fast rates, and of course, for the other parameters, you just get a parametric rate. And of course, in this particular case, there is a lot of additional nice information that the parameters of the problem are asymptotically independent of the change point, and you can also calculate confidence intervals because essentially everything is known about the asymptotic distributions. So for the VAR model parameters, we get exactly the rates that I showed you before. But for the change point, it's not only the log p price that you have to pay because you are in this high dimensional regime, but you also pay a log t price. And for a long time, I was thinking that the technical tools that I was using are not adequate, but it seems that this is a fundamental feature of these high dimensional problems, and you cannot avoid this extra penalty. On the other hand, the nice thing here is that if your transition matrices have a lot of signal, essentially it's fairly easy sort of to locate the change point. But I think this is sort of a fundamental issue. And the question is how this propagates when you really have the true problem that you would like to solve with multiple change points for having a really dynamically evolving network, the problem that Eric addressed. He provided some consistent estimates about the parameters, but he didn't really say much about, the multiple change points. He has an algorithm, but I suspect that how this propagates, I have no clue at this point. But I wanted to make sort of this point because this shows a fundamental difference than the low dimensional problems. So high dimensions have a number of technicalities. Let me skip some of these things. So in the last 5 minutes, I would like just to very briefly talk about some extensions. So these are the 3 problems that we have results. I don't know if I am going to have any time to talk about Bayesian VAR inference, but I would like to show you a few things here because this, I believe, are useful for applications. So actually this extension, so right now I'm trying to extend the model, and this came up from a practical consideration. I was reading some papers in economics, and people have been wondering about this type of relationships. So right now, up to this point, what I would like to do, or what people try to do is, if you sort of start separating your variables and you treat them as 2 separate blocks, can you sort of tell how this block of variables influences this other block of variables? And the main question is, why don't you pack everything into a big VAR model? Well, because for example here, in this particular application, which was the starting point, you have microeconomic variables that capture the real economy, and then you have the stock market that captures sort of the financial sector and just something very different. In another important application, if I have omics data, one of my block of variables are the gene expression data, and the other block of variables are the protein expression data. And I know that, if I put all of them together, personally, I don't feel very comfortable. I would like sort of to keep them separate, model them appropriately, and see how one influences the other. At the end of the day, this is, if you think about it, I would like sort of to be able to develop a test between blocks of time series. This test exists for 2 time series. This is exactly the classical Granger causal test, or this F-test that I've told you briefly about, but can we sort of do it in this bigger framework? So this is my framework. In this case, I have 3 sets of variables, and of course, if you look, the arrows have a very particular structure, and here is exactly the model. Essentially, I'm modeling them as a recursive system, and in economics, having these recursive systems is fairly kosher, and there is explanations of why. So in this particular case, the first block of variables evolves according to a VAR model in its own happy way. But the second set of variables is influenced by the first set of variables through this B matrix, and then it also has autoregressive dynamics. And for B, we can be fairly agnostic. For some applications, a low-rank structure may be appropriate. For some other applications, a sparse structure can be appropriate. And here I'm putting everything together, and I'm also assuming contemporaneous dependence between the two components. So if you look at the second equation, and you may have encountered in some econometrics papers, this is the var x, where x starts for exogenous variables. But here I have it in a more general setting as a recursive linear dynamical system. Okay, you need to solve all these problems with lasso penalties, and if you have assumed low ranking, you throw nuclear non-pernaties. All this is fairly standard. The rates, here are the full rates, even for the contemporaneous dependence. Nothing surprising there, all the things that we discussed. Again, here, nothing particularly surprising. The only interesting thing is that the exact bounds for the parameters that come up only in the second part of the system, as you expect, have very intricate dependency also on the cross spectrum between the two blocks of variables. So you need to be fairly careful. There are a lot of dependencies coming from all over the place. You have temporal dependence within the X set of variables, you have temporal dependence and cross dependencies within the Z set of variables, and then you have cross dependencies between the two blocks and so on and so forth. So actually we applied this, and it turns out, actually the applications potentially has serious implications for policy, whether the stock market drives, so for example, if there is a very strong downturn of the stock market, which is the X equation, and if that starts driving the economy, that means that there is a very different set of policy rules that need to be adopted, as opposed to if it's the other way around. So trying to do some additional work here potentially is important for application. So it's not just a trivial extension, just to do some technical work. I don't have any time to show you, but essentially we have right now, I have started thinking much more of how we can develop a proper testing framework going beyond rates and so forth. I'll skip that. It's not particularly, it's very similar to the previous piece of work. So the last thing that we are working on is, what I have found out is, if you are in a single realization classical economic time series, and you don't have adequate data because at some point you run into problems of stationarity, even if you tune your parameters, your lasso parameters, the penalty parameters as well as you can, sometimes the estimates are not that great. And I start asking what happens when you go the Bayesian route. So this is some new work with my new colleague in Florida, Shiti Karaj, who is an expert in Bayesian inference. So we looked at this problem. We have some limited results up to this point. These two types of prior distributions, here are all the technical details. Essentially, this is the conjugate prior, so computations are very straightforward. Here is a hierarchical matrix prior. You need to resort to a standard MCMC algorithm, nothing particularly interesting here. But this matrix prior has as particular choices the group lasso that Parker and Casella discussed, multivariate distributions, Wishart distributions, and so on and so forth. And this is the only technical result. As you can see, the main thing is that we can establish consistency of the posterior distribution, but the scaling, the high dimensional scaling, is much, much slower than what we had in the frequency case. And we are even more restrictive when we go into this non-hierarchical prior. The key technical result is the key concentration inequality that I showed you, essentially this Hanson-Wright type. You need to further extend it in order to be able to turn the crank here. Where do we go from here? I think developing testing procedures, given all the applications that we have seen, especially in neuroscience, is a worthwhile exercise. I've already mentioned multi-change point VAR models. You see that even for a single VAR model, for a single change point, there are a number of technical challenges coming in. The question that was asked at some point, what about, are the relationships linear? What about nonlinear models? Of course, the question is, what you mean by nonlinear? Which class of nonlinear models you would like to study? And something that I would like to draw your attention, because Daniel Bass's talk essentially made a lot of connections. High-dimensional VAR models and control. It's a very, very open field. There is a very complete theory of linear VAR models for low dimensions, but the moment you start going with high dimensions and you have sparsity or other structures, very little is known. And actually, this is a very new journal that, you know, they created the IEEE, these are the engineers, they create exactly to start studying this type of problems. And a number of interesting papers have started showing, appearing here. So I think, you know, in that previous talk, the issue of control for the brain was a very important question. But at the same time, if you're trying to do control and estimate the parameters, because in many engineering systems, the A matrix is given to you by whoever designed the system. It's an engineer system, it's a man-made system. But, you know, in neuroscience, the connections are not known to you, so you need to use the data both to estimate the parameters and at the same time understand what are the appropriate controllers. And we have already seen a number of technical difficulties just to estimate. So when you couple the two, essentially nothing is known. So I think that's a fruitful area. So all this work was done, I mean, the main technical results for the frequency scales were done by my previous student. This is work with current students, one in my new place, one in my old place. And thank you very much for your attention.
Questions?
Yes, please.
So if you do have covariates, where would you use those covariates in the kind of model?
For which problem?
I mean, if you have a VAR,
Yeah.
okay, so your stock markets and also economic variables, they have in fact the other covariates that also define all these relationships.
Yeah.
And then where would you use those information in the formulation of this network?
So this is, let's say, the stock market evolution, standard VAR dynamics. This is the macroeconomy evolution. So you see that I believe in this formulation, and that's why I would like to have the ability to test whether this is the true relationship, whether information from the stock market seeps in and influences the dynamics of the real economy. So if you think of a more biological application, here I have the gene expression data because essentially they encode for proteins. Here I may have my protein expression or metabolic information, and therefore I believe that by incorporating information from the gene expression compartment, I can understand better the dynamics of the metabolic compartment. But at that point I would like not to throw everything into a gigantic VAR with 2,000 variables, but I would like sort of to keep them distinct in order especially to be able to test whether this makes sense, this is 0 or not 0. That's why we looked at this type of test.
I think in the genomics applications, the number of time steps that people have is usually quite small.
Yes.
And so my question is, what do you think of that? And in the asymptotics, or your results, maybe they're not asymptotical, but at least there are some parameters you can play with.
Yes.
Is it comparable to ordinary regression? If you do the lasso on expression, then you may have a couple of hundred or maybe even thousands people and then a lot of parameters. But in the time setting situation, it seems a bit different. You have few time set, but also at every time you have more observations.
Yes.
Maybe. And
so as I pointed out in one of the slides, the moment you go to the panel VAR, in the neuroscience domain, as we heard some talks, things seem to be fine because they have a lot of time points and also they have a lot of subjects. So you have both independent replicates and hundreds of time points. As you point out, in the functional genomic case, you need to be careful because, as I said, usually time points are 10, 15, maybe 20. And then the name of the game is how many replicates you have. So for example, if you have a mouse model, people may just have 5 mice because it starts becoming expensive. And at that point, but brings another very interesting question. What happens to a VAR model where you only restrict it to a subset of the variables, although So you are only focusing on a few important pathways and you are only looking at, let's say, 50 or 100 genes, although you know that there is all this other universe of genes that you are throwing out, and you know that somehow they impact your model. So essentially you are working in a misspecified type of setting. These are sort of, from a very practical application perspective, the most challenging settings because your n is fairly small. If you have cell lines, you can do more replicates and you can go up to n equals 10 or 15. So that's not, I mean, you can compensate, but this is sort of, I would call it a very fragile regime where you need to be very careful.
And if you had a choice between more replicas or longer time, more time lags, what something you can say?
Yes, in that case, so, you know, once you turn the crank, the more replicates definitely start giving you more information because it's independent information. But then you need to be also careful because if you have a few time points, you may not be able to capture the phenomenon and understand, you know, how temporally, you know, the biological mechanism evolves. So there is always kind of a balance because if in some cases we looked at some data produced by a collaborator and he only have 5 time points and essentially we don't see anything. You know, the resolution is not adequate. So you know, you need somehow a priori to know that even with this limited temporal resolution, you're gonna see something interesting. And at the same point, once you know you have the appropriate temporal resolution, hopefully based on prior knowledge about the dynamics of the underlying phenomenon, they're compensating with more replicates, but will do the job. So the neuroscientists actually, from what I learned in this workshop, are in a great setting because you know they can go down to very fine temporal resolutions. My only concern there is that you need to be careful whether you have really stationary data or then you need to start fitting a multi-change point, you know, the model that Eric talked about, because having 800 stationary points, I haven't encountered them in life myself, but maybe I've been looking at the wrong domain.
I mean, you already mentioned that the problems with non-normality, effectively. But I guess especially in the type of the analysis you showed, which was the 2006-2009 financial situation, there probably was lots of time or tail dependence, most likely. Could you see that in, or is that something you could test for?
You know, that's a difficult question. So for financial or for this type of variables, this paper in JASA, actually by 2 econometricians at Princeton, you know, they have a whole set of recipes of how to transform the data to bring them as close to normality. So at least, you know, for this type of application, I can just follow the recipe, and there's extensive work. But for other applications, and especially when you start veering off to more financial type of data, heavy tailness is there. Unfortunately, for heavy tail data, we don't know anything about IID data.
Yeah, but it's not even that, they're also tail dependent.
Yes,
Yeah.
You know, maybe 10 years from now, we can gather back together and have more results. But you know, anything that starts going with more heavy tail, nothing is known.
Okay, the last question? No?
All right, thank you very much.
I think it's time for tea break. We will be back at 11 and let's thank George again.